Hi, my name is Joe Kramer. I'm an OpenSciEd high school physics teacher and a writer on Unit 1. This is lesson 3 of Physics Unit 1. This is the lesson where we start to look at energy more explicitly as a resource, and students start to investigate how real data from Texas can inform our modeling. We begin to build what will become a central model in our investigation of energy transfer. Let's take a look at what that looks like. First, some details about how we got to lesson 3 from lesson 2. In lesson 2, we used power strips to model buildings, and then we connected them to a central power strip to model a substation. We looked at how short circuits and broken circuits could cause lights to go out in whole neighborhoods at once, and how safety features can limit the scope of a power outage if they're working correctly. So we leave lesson 2 wondering, could short circuits and broken circuits explain why people lost power in Texas during the storm? Some broad details about the lesson. Lesson 3 is an investigation lesson that takes about 3 days. It's not a hands on materials lesson like the power strip dissection, so it will take less than 45 minutes of material preparation. But it is very much a minds on lesson where part of our work as teachers is to convince students that their own ideas matter for figuring out the answers to questions that we have. I'll talk about a few key points in this lesson in three main chunks over these 3 days. Near the end of day 1, we introduced some simple conventions for representing energy transfer. This is what we call the energy transfer diagram, and we're left wondering what this energy transfer might look like during the Texas storm. We start day 2 by modeling a few possible scenarios, and we share our ideas on how these models can help explain and communicate our ideas about energy transfer. This is where students start to suggest their own creative ways of quantifying how much energy goes where in different scenarios. So we're left wondering which of these scenarios actually explains what happened in Texas. And then to finish day 2, we look at actual graphs of predicted demand for electricity, and we see that people wanted to use a lot more electricity than usual during the storm. We begin day 3 by looking at graphs of supply alongside this predicted demand, and we see that power plants couldn't keep up the supply that people wanted. So we circle up and we come to consensus on how to model a couple of scenarios that match the data that we have. So, in summary, we figure out these energy transfer models can say a lot. They can show conservation of energy, and they show the amount of energy limits what can happen in a system. From the graphs, we see that the production of electrical energy must match the electricity used. And we see spikes during the storm because people needed to heat their homes. However, power plants couldn't supply enough energy, which we think is part of the reason why people experience blackouts. I'd like to highlight a few key moments from these 3 days. First, this is what an energy transfer model might look like early on. We put components in boxes. Energy transfer is shown with an arrow from one box to another, and then we bound the system using a dotted line. Simple is good here. We do not want students spending a lot of time making detailed pictures of houses and power plants. We want students to draw these diagrams quickly and focus on energy transfer. These models can help us identify key questions. For example, in this example, we're not quite sure whether house 1 and house 2 get zero energy or just less energy. So we put a question mark on those arrows. And the concept of a system can be rather nuanced. So when we make our first energy transfer model based on the reading at the beginning of day 1, this tree in the story makes for a good place to discuss what is considered in the system versus out of the system. That will pay off later for our broader systems thinking. Then on day 2, we use these conventions to model scenarios related to blackouts and energy use. It's a great thing here for students to propose their own way to show how much energy goes where in the system. You'll see lightning bolts or dots or numbers or arrow thickness. Try not to encourage everybody to use one type of method to show energy quantity. You'll have a chance to come to consensus as a class later on day 3. At the end of day 2, we see that the amount of electricity the power company expects people to use is changing all the time. And we see that there is a big spike in this predicted demand during the storm. That's what I've circled in red here. Temperature dropped to 22 degrees Fahrenheit, so we think people wanted to use electricity to heat their homes. Then on day 3, we see how much electrical energy was actually produced. When we compare electricity production to the previous year, we see that production during the storm actually did increase a lot, but it couldn't keep up with the huge increase in predicted demand that was greater than a normal year. So to conclude day 3, we circle up as a class to come up with our own example scenario models that actually match the data we have. For example, in this diagram, one source stopped working, so house 2 and house 3 wanted more energy than they could actually get. We also come to consensus on one or two methods of showing energy quantity. In this example, we're using numbers, but your class might decide differently. Where do we go from here? At the end of lesson 3, we're wondering what sources are actually used in Texas because the power plants clearly knew this increase in demand was coming. It seems like some sources must have not been able to do their job, so we wonder which types of plants are to blame. Some tips and tricks to keep in mind. It's okay to introduce these conventions in a top-down way. You can just tell them to use these conventions so that you see consistency across your different sections of your course. However, on the scenarios handout, try to give students space to develop their own conventions for energy quantity. This early in the year, we're still convincing students that their own ideas really do matter, and they tend to have strong ideas about this aspect of the modeling, so go with it. Percentage numbers, however, can be tricky. The power supplied by the power plants is not going to stay consistent. So if students try to make that first number coming out of the power plant 100%, this won't match up with the data. During the consensus discussion, you can guide students away from using percentages if they don't realize this on their own. Some energy quantity conventions really do matter. So when you're agreeing on how to show how much energy goes where, it's important to label the quantity on the arrows, not on the boxes, because we're focused on energy transfer. And it's important that energy into a component is equal to energy out of that component. So in this case, we see 6 energy units going into the substation and 6 coming out. Note, we will often use these energy transfer models to identify where we have questions and where we want to investigate more. So keep using question marks for this purpose. Keep in mind during the scientist circle, what is most important is that the models make sense to students and students can draw these models quickly to communicate with each other. We'll be using these diagrams a lot as the unit goes on. A couple of details about terms that come up. We construct these diagrams together and then we refer to them as energy transfer diagrams on assessments. So students need to understand what we're asking for in these diagrams. The terms constraint and design criteria come up around the engineering design tracker, which you can see right below my picture here, but I didn't talk about. This comes up on day 1 in the context of undergrounding power lines, and the theme of constraints and criteria continues throughout the unit. Then demand or electricity demand forecast versus supply or production come up in the context of these graphs. Notice that we refer back to our initial consensus model here. We realize it's basically an energy transfer diagram with some detail added. And then we use these conventions of these energy transfer diagrams throughout the rest of the unit. So it can be helpful to have this poster with 1 or 2 scenarios on the wall so that students can refer to it when making their own diagrams in the future. So parting thoughts on lesson 3. This is where students start to build more sophisticated energy modeling techniques that we'll use throughout the units. Investing in your class culture at this point means truly valuing students' input on these models. So I would say patience and curiosity on your part will pay off down the road. Thank you very, very much. I'll be back to talk about lesson 4.